Hey kids, welcome to day 2 of volume by revolution. Okay, so anytime you're asked about a volume problem, you want to look for the words revolve around this line, revolve around this axis, because the last kind of volume that we're going to do is not a volume of revolution. But we are going to do the second volume of revolution. And what differentiates this from the disc or potato chip method is that there is going to be a space. So here's what I mean by that. Find the volume of a solid bounded by a curve that's a parabola and a line with a negative slope that is rotated around the x-axis. So that's my axis of revolution. So just like before, sketch the region bounded by the curves and sketch the axis of revolution. So here is my line, y equals negative x plus 3. And here is the curve. Y equals x squared plus 1. And I chopped it off where they met. So the bounded area between them is how I'm going to start. And I'm going to use this area to find the volume. So my axis of rotation is the x-axis. Find the points of intersection. How do I find the points of intersection? Right? To set those equal to one another. So I have x squared plus x minus 4 is equal to 0. I'm sorry, minus 2, silly. So this is 1, and that's negative 2. Draw the reflection of the shape over your axis of rotation. Okay, so I have the image across the axis of rotation. And now I'm going to draw the strip. Remember, my strip has to be perpendicular to the axis of rotation. Perpendicular to the axis of rotation. So there's my strip. I have my top minus bottom. Take your strip and draw it in your image. And revolve. Revolve the top. I'm going from the line to the image of the line. Revolve. I'm going from the curve to the image of the curve. Revolve. That, my friends, is not a disc. You know what that is? That, my friends, is a lifesaver. Or a bagel. It's got a hole in it. It's got a hole. Do you see? It has a hole in it. It's like a donut. It's like a bagel. It's like a lifesaver. So the space, do you see how there is a space between the shape and the axis of rotation? We didn't have that yesterday. Yesterday, we had shapes like this. The axis of rotation, the shape was smack up against the axis of rotation. There was no space when you spun it. This time there's a space. An empty space is going to make a hole. Well, what if you didn't have an empty space? What would the radius of the first the large circle be? Going from the axis of rotation up to the line y equals x minus 3. What about the radius of the hole? So the long line was the radius of the donut. The short line is the radius of the hole. Oh, I forgot I drew that. Right, there's my pretty lifesaver. The space between the 2D shape and the axis of revolution creates a hole in the 3D shape. So remember, you're going to be making lots and lots of lifesavers, right? Because you're going to click and drag that strip and you're going to draw another lifesaver here, but they're all going to have a hole. Oh, it's so terrible. And you're going to sum them up. Sum them up, you find the volume. The volume is a difference of the area of the big circle, suck out the area of the small circle to create your hole. Okay, this is your big donut, solid donut. Suck out the donut hole. Now with the properties of integrals, the integral of a difference, right? You can put them together, right? So the big circle is pi big radius squared minus pi little radius squared. And then these are your thicknesses. Sum all of those volumes up and you get the volume of the shape. So my big radius came from the line, right? The top of the big radius was the line. So that's minus x plus 3 squared. And the small radius came from the curve, right? This small radius came from the curve, x squared plus 1. Osmosis the pi out front. Combine the integral of a difference is a difference with one integral. Put on your x numbers of intersection that we found. The radius is in terms of, big radius is in terms of x, little radius is in terms of x, so I am integrating dx because my strip is pointing at the x-axis. And now I can just do calculus, put it in or put it into my calculator, and I got 23.4 pi. They didn't give me units. I don't have to give them units back. If you want to multiply times pi, that's fine. Just make sure you write 3 places past the decimal. In reality, the disk and washer method are the same. Do you see that? The disk and washer method are the same. Because if I had a shape like this, I drew its image here. I drew my strip. I would be integrating. My big radius would be the function, let's say whatever function that is, pi r squared minus 0 squared, right? The small radius, there is no hole. So no hole means subtracting 0, right? No radius. Solid. Potato chip, disk. Nicely done. Let's do another one. There's a lot going on here. So find the volume by rotating. That's a volume of revolution. Where do they want me to rotate? X-axis. Here's the region that they care about. Below root x, above the x-axis, bounded by x minus 2. So I drew my image. Oh, I forgot my axis of rotation. So my axis of rotation was the x-axis. And then I drew my image across, and then I drew my strip. But hey, do you see my question mark bouncing up and down? Why do you think that's bouncing up and down? Look, for this part of the shape, there's no space between the shape and the axis of rotation. So what do I have there? I have potato chips, right? That is when I have no hole. There's no hole when I spin to the image. That is a solid disk. So the first region is just going to be, right? So really I have R1 and R2, because what's true about R2? D2. When you draw a strip here and a strip in the image, you've got a space. So you need to add those two together. So I'm going to stop at that number. What do you think that number is, though? That's where the x-intercept of x minus 2, right? So that's going to be 2. Ah, darn it. I didn't want to do that yet. Shoot. I wanted to say region 1. I'm going to do disks because there's no hole for region 1. So I'm going to go from 0 to 2. What's my radius? My radius goes from the axis of rotation to the function, but that's just the x-axis to the function. But I'm doing a circle, right? The area of a circle is pi r squared multiplied by dx gives me my width, sum them all up. And then I'm going to add R2, which is the washer or the lifesaver. So I need to go from 2 to 4 of big radius. Where's my big radius come from? Big radius squared minus little radius squared. Don't forget your pi. My strips are perpendicular to the x-axis, the axis of rotation, so dx. My big radius comes from what? Square root of x. But this time I have a small radius. What does my small radius come from? So I would have to do 2 integrals because I have 2 situations. I have a situation where there is no space between my bounded area and my axis of rotation, but I'm connected to a place where I've got a space between my axis and rotation. Now this point of intersection is at 4, right? Can you see that? The square root of x, when does it equal x minus 2? I mean, I can do algebra on that. Square both sides, which means I got x squared minus 4x plus 4. I have an x here, right? But hopefully you can see that when you enter 4, the square root of 4 is 2. 4 minus 2 is 2. So this x coordinate is 4. So what I wanted to show you was I could do this, absolutely, get my answer. And my answer is 16/3 pi. This answer was 8 pi. This answer was 8/3 pi. So add 8 pi and 8/3 pi, and you get 16/3 pi for my total. But in this case, there was a more efficient way to do this problem. What if I wanted to go all the way from 0 to 4? If I go all the way to the 0 to 4 with the disk method, don't you agree that I've got too much space there? Right? I would include this space, which means, of course, I include this space and I include the spin of that space, right? In my three-dimensional. Because this boundary is straight, can you tell what geometric from your high school geometry, your middle school geometry class, can you tell what that is? Well, that's a cone, hon. Do you remember what the volume of a cone is? The area of the base times the height. Can you see what the height of my cone is? Can you see what the height of my cone is? That's the radius, sorry. Radius I meant, and height. So there's another way I could do this problem, which is do the disk method and subtract out that cone. So do the disk method all the way across, which is too much volume, and then subtract the cone because the edges were straight there in your 2D shape. And if you do that, that's going to get you pi. Oops, I forgot. This is a cone. What do you have to shrink by? 1/3, right? So that's pi times my radius times my height multiplied by 1/3. So this is 8 pi. This is 4 times 2 is 8. This is 8/3 pi. And you would get 16/3 pi, just like you got doing it the disk and lifesavers method. Oops, sorry, I didn't mean to go that quickly. Okay, so 2 ways. Region 1, disks, plus region 2, which was lifesavers, because you went from 0 to 2 and then 2 to 4, so you had to add those two together. Or you could do the disk all the way from 0 to 4, pi r squared, subtract out the cone. Pretty cool. So again, this application of slicing perpendicular to the axis of rotation is called the washer method. There you go. If you are slicing perpendicular to the x-axis, but you have space between your shape and the axis of rotation, you're doing your washer method. Please be very, very careful. So in this instance, you are slicing perpendicular to the x-axis. So your limits of integration are x numbers, your functions are in, your radii are in terms of x, and you're integrating dx. If you are slicing perpendicular, slicing down or towards the y-axis, then your limits of integration are y numbers. Your radii are both functions in terms of y, and you're integrating dy. Both of them have a pi on the outside that comes from the area of the circle. Pi r squared, right? Add them up. Please, 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 please make sure you know your algebra. Don't you dare. Don't you dare claim that, oh, I can just take big radius minus small radius and then square. AP will not follow your work after this. This is, remember, I try to tell you about these. You get no follow-through points. If you do this math from the beginning of your setup, I don't care what your math is after that, how nice, how sophisticated, how correct after this, they will not read your work after this. They can call this an egregious mathematical error, right? That is not true. You know that, right? This is not true. No. The disk method just means your smallest radius is 0. You have no hole, so you don't have anything to subtract off. Right? So again, you're either perpendicular to the x-axis, and your axis of rotation is parallel or is the x-axis. Here, you're slicing perpendicular your axis of rotation is parallel or is the y-axis. I didn't really draw that right. The strip you draw for the washer and the disk method is always perpendicular to your axis of rotation. Always. I highlight that because in our next revolution, volume by revolution, we're going to talk about when your strip is parallel to the axis of rotation. For washers and disks, the strip that you draw in your region is perpendicular to the axis of rotation. Perpendicular to the axis of rotation. If your axis of rotation is parallel to the x-axis or is the x-axis, then your radii formulas, both capital R and little r, are in terms of x. Your limits of integration are x values. If your axis of rotation is parallel to the y-axis or is the y-axis, do a little bit better job of drawing. Right? You have your lifesaver, and your strip is pointing at the axis of rotation. As long as if your axis of rotation is the y-axis or parallel, your strip is perpendicular to it, then your big R or your little r formulas are in terms of y, and your limits of integration are y values. So let's try one of those that's a y-axis situation. So I have a region bounded by these two curves. One is a line, one is the curve y equals x squared. I want you to find the volume by revolution. I am revolving around the y-axis. If I'm going to do washers, and notice that I'm going to do washers because there is a space between my region and my axis of rotation. Right? There's a space. So that's what kind of looks like, you know, when you go to like Carmen's, right? And they dig, or any ice cream store, and they kind of dig into down into the dig out and scoop out your ice cream or your Carmen's. I mean, they always kind of leave stuff on the side. That's kind of what this 3D shape looks like. I'm going to draw my strip that is perpendicular to the axis of rotation and spin it. Spin. Because I had a space between my 2D image and the axis of rotation, I have a hole in my lifesaver. The volume of that lifesaver or washer is the big circle minus the small. That gets me my area. Multiply times thickness to get volume. Notice the thickness of my strip comes from changing a y value, which is why I'm dy. I did factor out my r. Do not, quote unquote, factor out that squared. You can't do that. That's not legit. Big radius, small radius. Integrate dy because my strip is pointing at the y-axis. All of that has to be in terms of y, though. Notice that my original functions are not in terms of y, they're in terms of x. So I have to go up to each one of my functions and get x by itself. I took algebra 1, I can do that. This is in the first quadrant, so I have the positive square root of x. Y is equal to 2x, get x by itself. Set it up. Who is my big radius? My big radius comes from the curve. Which one of these is the curve? My small radius, the radius of the hole, that's from the line. Whoops, I didn't mean to cover up the x. So volume is equal to pi, which you can osmosis out here, big R squared minus little r squared. Here's my little r. Here's my big R. And there's my constant pi. In a rubric, the constant pi and the limits of integration would be worth 1 point. The integrand would be worth 1 or 2 points. Usually if the integrand is worth 2 points, they don't put a point on the answer. If it's worth 1 point, they'll give 1 point for the integrand and 1 point for the answer. This one was easy enough to do by hand. Coinky dink, I got 8 pi over 3. Had a lot of 2's. So we're going to create some 8's. Cool? One more. And what I want to show you here is, remember that I have the same region. I also want to rotate it, but my axis of rotation is x equals 2. This is my axis of rotation. So be careful. Right? With my axis, I still draw my strip, but I draw my image across the axis of rotation, draw the image of the strip, get my large radius. Who's the large radius? This is hard. This is hard to picture. The large radius, I can see it, but remember, your radius is measured from your axis of rotation all the way to your farthest boundary. And you want to go to the boundary of the actual shape, not the image. How long is that? Well, I don't know. Now my strip is still perpendicular. My axis of rotation is parallel to the y-axis. My strip is perpendicular to the y-axis. I'm going to be integrating dy, so I know this is going to have to be x equals y over 2. And this is going to have to be x is equal to the square root of y. How long is that? What is that? Isn't that 2? Is 2 too big or too small to be the radius of that circle? It's too long, right? So how could you write an expression for my big radius? The big radius is going to be 2 minus, right? Minus what? This part, right? That's kind of hard. That's kind of hard to see, I know. This takes practice. Now let's do the small radius. There's the small radius. It's kind of floating out there in nowhere land. Remember, all my algebra expressions measure from an axis. So x is equal to, I have to go all the way to the axis of rotation, right? That radius, isn't that also 2? That's still a distance of 2, but the little radius is 2 is too much. What do you want to subtract off? You want to subtract that off, right? What is that the distance to? The curve. Right? So you see why your drawings are important? It doesn't matter if your drawings are good or not. They just have to be enough so that you can figure out that the process never changes. Right? So the outer radius is 2 minus y of the line. The inner radius is 2 minus the curve. The volume is y equals 0 to y equals 4. Pi, capital R squared minus little r squared, strip points at y-axis. There we go. Again, probably wouldn't have to do this by hand, but just to show you that I could. Oh, look at that, 8/3 pi. Again, have a lot of 2's hanging around. We'll do some more practice in our next live session.